Good evening and happy Monday. We are going to be examining derivatives of exponential, logarithmic, and trigonometric functions this evening. So block A, the first block of this evening's meeting, will be the exponential and logarithmic functions. Then block B, the second block, we will be looking at trigonometric functions. Okay. So derivations for everything is provided in the videos on my math. Okay, so the derivative of the exponential function. So remember, the exponential function is any function of the form b to the u, where b to the x, where b is a non-unitary real number greater than 0. The natural exponential function, e to the x. In this case, I'm doing the general, so e to the u. Derivative is u prime, e to the u. Derivative of a more general exponential function, b to the u prime times b to the u times the natural log of b. Logarithmic function. Yeah, we're going to start with the natural base. d dx of natural log of u is just u prime over u. And of a more general log, say log base b, d dx is u prime over u times log of b. We're just going to differentiate some functions. H of t given as e raised to the 3t squared plus t minus 1. Right? H prime. Be u prime, so the derivative of the exponent, and then times the original function. So we want the derivative of 3t squared plus t minus 1. What is that derivative?
Six t plus 1.
And then times our exponential. Right, there's the derivative. The quantity of log x plus x squared raised to the third power. Right. General power rule. Gives us 3 times the quantity natural log of x plus x squared, right, raised to the second power. The derivative of what's inside. Derivative log of x. Right, well, it says it's the derivative of what we're taking the log of over what we're taking the log of. Derivative of x is just 1. And then just plus the derivative of x squared 2x. Right, you can leave it like that, or you can rewrite the order. right? Or you could write it as a single fraction. Doesn't matter. Two raised to the x squared plus 3x. Or x cubed, I'm sorry, it's x cubed plus 3x. Right. Clearly, this is an exponential function. What is the base for the exponential? But what is the base of the exponential?
Two.
Right. So we know we're going to have the function times log of 2 in the derivative. Right? It's right here. All we need to do now is multiply that by the derivative of the exponent. Which is 3x squared plus 3. And there's our derivative. Natural log of x squared. There are two methods to this. First method. We take the derivative of what we're taking the log of. Divided by what we're taking the log of. Be 2x over x squared. This simplifies to just 2 over x. Second method. Use laws of logarithms to rewrite the function. We will get 2 times log of x. Now take the derivative. 2 times 1 over x, which is just 2 over x. For this problem, it really didn't matter, right? They were both relatively simple in terms of the algebra required. However, you may come across some log functions where, algebraically speaking, it's going to be a lot simpler to first go ahead and use the laws of logarithms to rewrite the function before you take the derivative. And I'll see if I can find some good examples of that. Okay, we look at the function. Ask yourself, what kind of function are we dealing with? Oh, perfect. At least let me do that. That's nice. That's a nice change. Knew it. There we go. Well, it's an exponential function. It's an exponential function that is not base e. Right, so the rule tells us it's going to be the derivative of the exponent, which is 1, times the exponential function, 4 to the r, times the natural log of the base, which is 4. That makes our derivative 4 to the r times natural log of 4. All right. What about this function? What kind of function are we dealing with? Did I turn on my work? Guess not. Let's do that now. Right, what kind of function do we see?
An exponential one.
What would be the base? There are two ways to go about this problem. Let's go over both methods. Right. Obviously, one method is going to be simpler than the other. The first method is to see this and just go, we have a quotient rule. Right? Remember what quotient rule said from Thursday, right? Yes. Take the derivative of the denominator. I'm sorry. Take the denominator, multiply it by the derivative of the numerator. Numerator is an exponential function of base 3. Its derivative would then be 3 to the w times natural log of 3. Minus the numerator times the derivative of the denominator. Denominator is also exponential, this time base 2. The rule tells us it's going to be 2 to the w times natural log of 2. And then all over the denominator squared. Now let's simplify it. There's a 2 to the w times 3 to the w common. Let's factor it out. We would then be left with natural log of 3 minus natural log of 2. There's a 2 to the W, common both numerator and denominator. So that simplifies. Three to the W times quantity log 3, natural log of 3 minus natural log of 2, all over 2 to the W. That can still be simplified. And if we really wanted to. I'll come back to it. That would be using quotient rule. Second way is you could look at this and you could go, as was mentioned, oh, this is an exponential function. Right? Then you just have to answer what base is it. Well, you had laws of exponents, laws of logarithms. You also have laws of exponents. And one of them will allow us to rewrite this function. There's 3 halves to the W, which makes this an exponential function base 3 halves. Rule then says it's the function times the natural log of the base. These 2 derivatives are they the same?
Yes.
They are, right? You just have to use properties of exponentials and logarithms. right? Three to the W over two to the W is 3/2 to the W. Natural log of 3 minus natural log of 2 becomes natural log of 3 over 2. Right? That means that now you're going to have to keep in mind those properties as well. Right? The properties of logs and the properties of exponentials. While not necessarily mandatory, they could make the problem a lot easier. Unfortunately, there's nothing we can do here to simplify. This is a quotient, which means we have to use quotient rule. Denominator times derivative of the numerator. Minus numerator times the derivative of the denominator. All over the denominator squared. Okay. Now it's time for algebra. Distribute the terms of the numerator through. And so distribute the 2 to the t log of 2 through here. Then distribute the negative 3 to the t log 3 through. Actually, it's going to be, no, those are going to be different. First property I'm going to use and then the second property. All right, remember those? That allows me to simplify 3 to the t times 2 to the t. That's 6 to the t. Two times 2 to the t and 3 times 3 to the t. 2 to the t plus 1, 3 to the t plus 1 respectively. Well, looky here, we have a 6 to the t log 2 minus 6 to the t log 3, right? If you factor out the 6 to the t, you're going to be left with log of 2 minus log of 3. Using the difference law for logs, that's log to the 2/3. Excuse me for a minute. Okay. Oh dear, now there's a massive slowdown. Okay, that's fixed. There's another way we could write this. So up here, instead of excuse me. So let's see if we can go longer than a minute without an interruption this time. Up here, instead of doing the property here, right? I could also use this law of logarithms. Right. So alternatively, we could write two to the t log of 2 squared, which is 4, minus 3 to the t log of 3 cubed, which is 27. Or alternatively, if you don't like that negative there, that'd be plus 3 to the t log of 1 over 27. All three of these are the same thing. They're all acceptable. This is where if you start to, say, compare your answers to what's in the back of the book, or compare your answers to, I don't know, you look it up, which you're not allowed to do, of course, on a quiz or a test. The answer form may look different than what you have, but what you have could still be correct. Right? So maybe you have this, but you compare it to the book, and the book has this. Right? Same answer, just different forms. So there are two ways we can approach this problem as well. I'm going to take the simpler route. Right, we have a monomial in the denominator, which allows us to say each term of the numerator divided by that denominator, right? Which we can now rewrite. Three halves to the w plus 2 to the minus w. This is now the sum of two exponential functions. That's very simple to do. It's just a sum rule. Right, first term, exponential, so it's the exponential function times the natural log of the base. Second is also an exponential function. However, it does have a chain rule involved. Derivative of negative w with respect to w is -1. So instead of plus, this is going to be minus. And there we go. There's the derivative. Unfortunately, what happens here if we try to do the same technique as with the previous problem. That term is still going to require quotient rule. Or product rule. So it's kind of meaningless then to rewrite this. Okay, so we kind of just draw a little sad face there, right? Might as well just work with the original function without rewriting it then. Oh dear, what's going on? Go away. No, don't share. Thank you. All right, quotient rule. Don't know why it keeps zooming when I try to write. It's getting annoying. Denominator times the derivative of the numerator. So it's going to be the derivative of the exponent times the exponential function times natural log of the base, and then just plus the derivative of x minus numerator times the derivative of the denominator. And then all over the denominator squared. Let's do some algebra. There's a 2 to the x squared common. So let's factor it out of the numerator. And then what we're left with in the numerator will be 2x, 3 to the x squared natural log of 3 plus 1 minus 2x, 3 to the x squared natural log of 2 minus 2x squared natural log of 2. Now, there's a couple ways to simplify this. Obviously, the 2 to the x squareds, they're going to simplify. So from there, we can either group the natural log of 2 terms, the terms with natural log of 2 together, or we could group the 2 terms that have the 2x, 3 to the x squared together. I don't think it's going to really matter. What I'm going to do is I'm going to group the terms with the 2x, 3 to the x squared together. That's a bummer. That's a +1. I could have factored out a 2 and simplified. Right, laws of log, we can write natural log of 3 minus natural log of 2 as natural log of 3/2. And then I can use that property of logs. 2 log of 3/2 is the same as log of 9/4. 2 log of 2 is the same as log of 4. So I can use those to simplify further. Any questions so far? Of course. There's a fun one. There's a lot of fun ones. Okay. Let's look at a nested natural log. Right, we want to find y prime. One over what we're taking the log of times the derivative of what we're taking the log of, which is going to be 1 over what we're taking the log of times the derivative of what we're taking the log of, which would just be 1 over x, right? That would be the derivative. Oh, it's a shame. Oh, I forgot I haven't done trig yet, so I can't do those. Darn. Let's look at. Let's look at this. And of course it zoomed out again, because why wouldn't it? So if we look at this, and we try to just use the logarithmic rule, all right? 1 over what you're taking the log of times the derivative of what you're taking the log of. That inside function, that's going to require a quotient rule, right? Which is a pain. However, we can greatly simplify this problem by just rewriting it. Laws of logarithms will allow us to write this. Well, that is much simpler, isn't it? We're going to have that constant 5. 5 times the derivative of the log, right? So it'll be 5 times the derivative of what we're taking the log of over what we're taking the log of. Minus 1/2 times the derivative of that log. Right? The derivative of 1 minus x is -1. There's our derivative. And then if you wanted to, you could try and write it as a single function. or a single fraction rather. I think I said function. Which would be that. If you went the first route that I was talking about, if you just started here and used the logarithmic rule, which would involve chain rule quotient, then this is what you should get after simplification. Right? Again, you could try and just use the log rule. But that inside function is a bit messy, isn't it? We can greatly simplify this. Plus. Rewrite it using laws of logarithms. Now take the derivative. Derivative of x plus 1 is 1, right? So it's just going to be 5/2 times the 1 over x plus 1. Derivative of x plus 2 is also 1. Right? And again, we can write this now as a single fraction. Minus 20x. We get 10 minus 20. All right, and that would be the derivative then, simplified. Start by writing this function with a rational, a fractional exponent. Y prime. It's a general power rule, right? Now it's times the derivative of that inside function. All right, now just do some algebraic simplifications. Looks like it's going to be 1 over 2t. Denominator becomes 4t square root natural log of square root of t. And it's 1 over all that. So how are we doing so far? Following along? Yeah, at least with the calculus?
Yep.
All right. And again, notice throughout all these problems, right? The algebra itself takes longer than the calculus. Which means if you're rusty on the algebra, you are not having fun right now. look at this one. Okay. Right? We take a look at this problem and we go, big picture, what's the function? It's a constant multiple, right? It's 3 times the function. Scalar multiple rule says it's going to be this constant 3 times the derivative of the function. Now look at that function. It's a base 8 logarithm. It's going to be what? It's going to be 1 over u times natural log of the base, right? Where u is the function that you're taking the log of. Now we need to look at the next function, which is a log base 2. Now let's simplify. Numerator is going to be just 3. In the denominator, we're going to have a t natural log of 2 times natural log of 8 times log base 2 of t. Right, so this bit here oh, that's not going to simplify. I'm sorry. I made a common mistake. That, unfortunately, is as nice as we can get it. Let's see if I can find. Some exponentials. I mean, not really. Yeah, this one could work. This function is an exponential. right? It's the function times the natural log of the base. Now times the derivative of that exponent, which is now a log base 2 function. Right, which is 1 over what you're taking the log of times the natural log of the base. Right, and that's just simplification. Are there any questions on the exponential and logarithmic functions? Okay. Right. I could keep going with exponential and logarithmics for another 10 minutes. But I feel like we've done enough of those types of problems. So I think what we will do is, if this were a regular 15-week class, I would just say, we finished 10 minutes early, whatever, have a good day. I'll do something similar, and I'll say, this block is going to end 10 minutes early. So you're going to have a 20-minute break instead of a 10-minute break. So when we come back at 7:50, we will look at the trigonometric derivatives. And at that point, we're going to have just about every type of derivative, right? There'll just be one function type left to look at after that, which is the inverse trig, which unfortunately I need implicit differentiation for, so that won't be until next time, I think. Right, that'll be next time. So break. I'll see you all again at 7:50. Okay, and we're back. Six trigonometric functions. Again, derivations are in the videos that are posted on My Open Math. sure that it didn't change my zoom level. Derivative of sine of u with respect to x. U prime times the cosine of u. Derivative of cosine of u. Negative u prime times the sine of u. Derivative of secant u prime secant of u tangent of u. Derivative of cosecant negative u prime cosecant cotangent derivative of tangent is u prime times secant squared. And then derivative of cotangent negative u prime cosecant squared. Now we're going to be dealing with differentiating functions that involve trigonometry, right? The trigonometric functions. We're dealing with a power function here, right? General power rule. Remember, bring the exponent down. So it's the power times the function raised to the power minus 1 times now the derivative of the inside function. Derivative of sine is cosine plus the derivative of cosine, which is negative sine. Right. Now, just like with the exponential logarithmic functions, if you compare answers, you may find that the answer the book gives looks different. Right, so for instance, I can rewrite this using properties of trig, using trig identities. Sine theta plus cosine theta quantity squared with appropriate properties, appropriate identities, becomes 1 plus sine of 2 theta. So you could see that as your derivative. Well, this one's fairly straightforward. We're dealing with a cosine function. So it's the derivative of what we're taking the cosine of, negative derivative of what we're taking the cosine of, then times sine of what we're taking the cosine of. Derivative would be negative 3 sine of 3x. Again, fairly straightforward. We're dealing with a tangent function. Its derivative is u prime. Times secant squared of u. 5 times secant squared of 5x. Another tangent function, u prime times secant squared of u Dealing with a sine function, right? U prime times the cosine of U. And if you wanted to write it as a single fraction, you could also write what you're taking the cosine of as a single fraction. It doesn't matter, they're all the same. So remember, this is how we would represent sine of 2t all raised to the fourth power. Right, so when we look at this function, we see a power function first. General power rule. Four times the function to the 4 minus 1. 4 times sine cubed of 2t. Times now the derivative of sine of 2t. Right? The derivative of a sine function. U prime times the cosine of u. So there are other ways we can write this. I just don't know if it's beneficial. I don't think it is. Wouldn't really simplify it, so I'm just going to leave it in that form. Again, notice that what we have is a power function. So we start with general power rule. General power rule will give us 3 times cosine squared of t squared plus 3t plus 1 times the derivative cosine of t squared plus 3t plus 1. Right. Derivative rule, negative u prime times the sine of u. Just rearranging terms here. We get negative 3 times the quantity of 2t plus 3 times the sine of t squared plus 3t plus 1 times the cosine squared of t squared plus 3t plus 1. So let's start putting now some logarithmic and exponential functions in with trigonometric functions. Logarithmic, natural log, is u prime over u. U prime, derivative cosine, negative sine, okay, then over u. Now this can be simplified. As a negative tangent of x. Five to the cosine of t, exponential of base 5. U prime derivative cosine. Times 5 to the u. times natural log of 5. We're now dealing with a product, right? So this is product rule. G of x times the derivative of f of x plus f of x times the derivative of g, right? Derivative of sine. U prime times cosine of u. Now we just rewrite it to clean it up. And there's our derivative. We're dealing with another product. But this time we're dealing with a product of trig functions. So there are two ways we can proceed from here. The most obvious route is to just use the product rule, right? G prime. Second function, so g of x times the derivative of f of x times the derivative of the first function. The derivative of cosine negative u prime times sine of u plus First function times derivative of the second, derivative of a sine, u prime, times the cosine of u. And now just cleaning it up. And there would be our derivative. Second method. Is to use trig identities first. Perfect. There's one in particular for this one. Just get it out. Identity for cosine of x times sine of y. It's 1/2 times the quantity sine of x plus y minus sine of x minus y. Using that identity, we can rewrite this as 1/2 times the quantity of sine of t squared plus 3t plus 5t minus 7. Minus the sine of the difference now. And then from here, we can take the derivative. By noticing, overall, we have a scalar multiple. Scalar times the derivative of the function, which is a difference rule. Derivative of sine. U prime times the cosine of u now derivative of sine again, u prime times cosine of u. And now just simplifying it. And there's the derivative. So the derivative function is unique, right? That means that a specific function cannot have multiple derivative functions, right? Its derivative, if it exists, is unique. There's only one. So what that means is what is highlighted has to be equal. They're the same. Through much algebra and trig identities, right, you can get, say, from here to here, or vice versa. I'll give you a minute to copy that. All right, while you're doing that, I need to take care of something real quick. Now that they have to copy something down and there's something important I need to discuss. So again, there are two methods. Can use the product rule. Or we can use trig identities. F prime, product rule. Second function times the derivative of the first function, right? It's u prime times cosine of u plus the first function times the derivative of the second function negative u prime sine of u. Now just cleaning it up. Right, and there we have it. Second method, trig identities. Right, in particular, that one. All right, rewriting using trig identities. 1/2 times the quantity sine of their sum plus the sine of the difference. And then we can take the derivative, just like we did in the previous one. This is now a scalar multiple. Scalar times the derivative of the function. Right? And then there's the derivative. So there are the two derivatives, same function, right? But the two different forms based on the route you decide to go down. Okay. Product rule, right? We have a product of functions. Second function times the derivative of the first. Now we're taking the derivative of an exponential function, specifically of the natural exponential, right? It's u prime e to the u. Plus first function times derivative of the second. Negative u prime sine of u. Now just cleaning it up. Going to factor out e to the 5t squared. Left with 10t cosine 1 over t plus 1 over t squared sine 1 over t. Right? Or if you wanted to factor out the 1 over t squared as well. Right? You would then have 10t cubed cosine of 1 over t plus sine of 1 over t. Here we're dealing with a quotient, right? So quotient rule. Denominator minus derivative of the numerator. Numerator is a sine function. It has derivative of u prime cosine of u. I don't know why I wrote a minus there. Times. Minus numerator times derivative of the denominator, which is a general power function, u prime times the power times the function to the power minus 1 and all over the denominator squared. Now we just have to simplify. Factor out the 5x minus 9 squared, left with 4 times 5x minus 9 times cosine of 4x plus 1 minus 15 sine 4x plus 1. And over 5x minus 9 to the 6th power. And then, of course, that can be simplified further. So I want to distribute that 4 through. And we'll be left with a 5x minus 9 quantity 4th power in the denominator. Right. Now, a mistake I see far too often. Would be something like this. Let's just go. Right. Or right. So remember sine, cosine, all of the trig functions, right? They're functions. Think of them like operators. So this is sine operating on 4x plus 1. It's not sine times 4x plus 1, right? Just sine, S-I-N, does not make sense. Right? And you can't just factor out either, right? You can't say sine of 2x is 2 times sine of x. It doesn't work that way. There are 2 ways to go about this problem. The most obvious way is to use quotient. Let's start there. F prime. Denominator times derivative of the numerator. General power function. U prime times 2 u to the 2 minus 1 minus numerator times the derivative of the denominator, a tangent function, u prime times secant squared of u all over tangent squared of 5x, right? All over denominator squared. Just try and clean this up. 8 times 4x plus 1 times the tangent of 5x minus 5 times the quantity of 4x plus 1 squared times secant squared of 5x all over tangent squared of 5x. Do I want to keep going? Or do I want to just leave it there? I think I will keep going. Factor out a tangent of 5x. We're left with 8 times 4x plus 1 minus 5 times 4x plus 1 quantity squared. All right, then we're going to have secant squared over tangent. All right, so if I do some scratch work, leave with a secant cosecant. And it'll leave us with this. Let's just leave it in that form for now. Okay. Method 2. Is to treat this as a product and use product rule. How could we write f of x as a product? Think back to the basic trig identities. One over tangent is cotangent, isn't it? So we could instead write this as the product of the quantity 4x plus 1 squared and cotangent of 5x. Which would now allow us to use product rule. Second function times the derivative of the first function, general power rule. U prime times 2 times u raised to the 2 minus 1 plus first function times the derivative of the second, cotangent u prime, negative u prime times cosecant squared of u. Right, and you should then easily see how we can get from that first derivative form to this. Are there any questions so far on the derivative of trig functions? Okay. So as with the exponential and logarithmic functions, while it's not exactly required, it may be beneficial to review and get comfortable with the trig identities. Let's take a look at this. So we're given f of x's cosine. We're asked to find the 100th derivative of f. Right, so remember what the 100th derivative means. Right, it'd be the derivative of the 99th, which is the derivative of the 98th, right, so on and so forth. Right, so let's just get started. Derivative cosine, we know, is a negative sign. Second derivative, right, would be that derivative, right, the derivative of what we just found, so derivative of negative sign, which is negative cosine. Third derivative would be the derivative of the second derivative, which is just sine. Fourth derivative, derivative of the third derivative, and that's cosine. Which gets us back to f of x. See that? So the derivative of cosine for lack of a better word, I guess, periodic, right? The derivatives repeat. Specifically, every fourth derivative starts the cycle anew. Since 100 is a multiple of 4, the 100th derivative of cosine is just going to be cosine. I'm going to do that. I'm just going to do this. Find the 201st derivative of sine of mx plus b. All right, assuming that m is a real number, or let's say both m and b are real numbers. Well, think about it. Sine's going to have the same property as cosine, in that every fourth derivative restarts the cycle. Well, 200 is a multiple of 4. So the 200th derivative of sine is sine again. But keep in mind that we're going to have 200 applications of the chain rule. What is the derivative of mx plus b? It's m, right? So every application of the derivative multiplies by another m. Derivative of sine is cosine, right? Specifically, it's u prime times cosine of u. So we have to multiply by another m. And so we get the 201st derivative is m to the 201st power times the cosine of mx plus b. Right. Can do something similar with the exponential functions. Right, once you know how they work. Let's go 6 to the x. All right, so for instance, the 50th derivative of 6 to the x would just be 6 to the x times log of 6 raised to the 50th power. Right? That 6 to the x, remember, every time you take the derivative of 6 to the x, stays. All that happens is with each derivative, you add another natural log of 6. Right, so these are some of the, so you might see these types of questions, right? You don't have to actually sit there, for instance, here and calculate all 201 derivatives. That would take forever. Just a little bit of thought and understanding of how the derivative of a specific function works should give you an idea of what the derivative is. Right, in this case, just a little bit of thought, understanding that sine, the derivative of sine is cyclical, right? It repeats every 4. And you're going to have to multiply by another m each time. You can easily get m to the 201st power. And then you know that, oh, well, I have 1 beyond the repeat of the cycle, so that's cosine. Are there any questions on anything we've done this evening? Okay. So tonight you have 3 assignments, assessments, rather. You have assignment 10 and 11 located on my math. They will be due on the 26th by the end of the day, by 11:59 p.m. Quiz 5 will be due the 26th by 6 p.m. Right, so it would be due before our next meeting, assuming that we would meet on the 26th. So as a reminder, there is no class on Wednesday. So as a comment, there is now a non-zero chance of the surgery being canceled on Wednesday. If it is, I have no idea when it's going to be rescheduled. So what's going to wind up happening is if they do decide to cancel the surgery, I will still not hold class on Wednesday, but we will then meet on Thursday, the 27th. Right, so what would wind up happening is I would push up all the topics by one meeting. All right, that is just in case they do decide to reschedule it at some other point this semester, this term. Right, and then I'd have to adjust for that and take some days off for that. If the surgery is canceled, I will post an announcement on Teams in the general channel stating that there will be class on Thursday instead of no class. If no announcement is posted, that means there's going to be no change. So make sure you check Teams. I can't give you a time because I don't know when. They haven't told us when to come in yet on Wednesday. So I would probably check Thursday morning. Again, if there's no announcement posted, then that means there won't be class. If they do cancel it, then I will post an announcement saying that we will be having class on the 27th, and then I will come back here and I will update the schedule to fit that. So I'm going to go right now under the assumption that we will not be meeting again this week. So everyone, please have a wonderful and safe week. I will see you all again, hopefully Monday, the 31st of July at 6 p.m. That means that the surgery went as scheduled and went perfectly fine. Just keep your eye on Teams for any kind of updates. I will see you all again the next meeting.
Thank you.
Thank you.